Momentum. You maybe heard this term before. Like if you go watch a football game, you'll hear maybe somebody gets tackled and they'll say, well, he had a lot of momentum. So momentum is a quantity that has something to do with speed, and it also has to do with mass. In fact, it is the product of those two quantities, those two measurements. So if you measure mass and you measure speed or velocity and multiply them together, you get momentum. So we could symbolize that as m times v. And v usually stands for velocity. And remember, in physics, velocity is a vector quantity. So direction is important. But sometimes we don't care about the direction, in which case we can just say mass times speed. So you just have to read the problem and see whether or not direction matters. So just a real quick example of how to do this. If a 1 kilogram turtle is walking in a straight line at 0.01 meters per second, what is the turtle's momentum? Well, if you identify the mass as 1 kilogram and the velocity or speed as 0.01 meters per second, you just multiply those two together and you get 0.01 kilogram time meter per second. Now you'll notice that unit, kilogram per meter, or kilogram times meter per second, that's kind of an unusual compound unit of measurement. And unlike a lot of other compound units, this one is not shortened. It's not usually named for somebody. I don't know why that is, but you may want to just keep in the back of your mind that this is very similar to a Newton, which is a kilogram meter per second squared. So the kilogram times meter divided by second is actually equivalent to a Newton times a second. Just keep that in the back of your mind. It might come in handy, a little fact there. So 1 kilogram meter per second is the same as 1 Newton second. Either one of those are acceptable units of momentum. So let's say you had a truck and a car going down the road. If they're going at the same speed or velocity, v, then the truck would have more momentum because it would have a larger mass. On the other hand, if the car were going faster than the truck, it's actually possible that the car could have more momentum than the truck. It depends on the product of mass times velocity. Your momentum is a multiple quantity. It's not a single thing. You have to measure two things. If neither the car or the truck are moving, then neither one has momentum because their speed or velocity is zero. It doesn't matter what your mass is. You have no momentum if you are not moving. So here's a truck and a roller skate, an old-fashioned roller skate going down a hill. If they are going at the same speed, then obviously the truck has more momentum. Could you think of a case where the roller skate and the truck would have the same momentum? Well, if the roller skate were going really, really fast and the truck were going really, really slow, then they could potentially have the same momentum. So I give an example here. A 1,000 kilogram truck going at 0.01 meter per second would have the same momentum as a 1 kilogram skate going at 10 meters per second. So momentum is just it's an indication of what we might call inertia in motion. Remember, inertia is a property of all matter. Kilograms actually is a good measure of inertia. It's your tendency to stay at rest or to stay in motion. Well, if you're in motion, then you have this quantity called momentum, which is your mass times your speed or velocity. Earlier, I did not give momentum a symbol, and I personally would probably give it a symbol just to shorten things up when I'm writing out my equations. But sometimes I hesitate to give it a symbol because the official symbol might be confusing to people. The symbol for momentum is the Greek letter rho. And it is not an R. It is actually, it looks like a lowercase p. So sometimes if you see kind of what looks like a P or an italicized P, if you're reading that in a textbook, for example, I'm going to assign a reading for this section. You'll see this, what looks like an italicized P. That's actually a Greek letter, and it's sort of universally recognized as the symbol for momentum. But like I said, you don't have to do that. That's just sort of the shorthand, so you don't have to write quite as much. So if you have momentum, it's because you're moving, but you can change your movement. You can speed up or you can slow down. So if you speed up or slow down, you've changed your momentum. Now, in order to change the momentum, you would either have to change your speed or change your mass. But in most cases, objects' mass don't change just because they're moving. You can think of examples where the mass might change. For example, let's say a meteor is burning up in Earth's atmosphere. Obviously, as it burns up, its mass is changing. But most things here on the Earth, most of the problems that you and I would encounter, the mass of the object stays the same. So we're going to focus mostly on changes in speed. Now, you may remember from earlier lessons that if you change your speed, we call that acceleration. But acceleration always requires a net force. Newton's second law. Acceleration is a net force divided by mass. So you can't have an acceleration without a net force. What that implies, ergo means therefore, is that any change in momentum must require the application of a net force. Interesting. The greater the force, obviously, the greater the change in momentum. Because if you have a great force, that means you have a great acceleration. If you have great acceleration, you have a great change in velocity. The bigger your change in velocity, the bigger your change in momentum. It's all sort of logic. It all kind of chains together. If you could take a force and apply it over a long period of time, you would get even more change in momentum. So a change in momentum actually involves two things, the force and the time that the force is applied. Okay, so both force and time are important in changing an object's momentum. Let's say you were pushing a car. That might require a very large force on your part, but you can take a car which is initially at rest, going 0, and maybe you can make it go 1 meter per second, let's say. That would require a certain amount of force. But if you could keep pushing for a longer period of time, you could accelerate the car even more. So if you push with the same force for twice the amount of time, then you produce twice the change in momentum. So earlier we said that momentum is mass times speed or velocity. Now we're saying that changes in momentum is force times time. We actually give that formula a name. We call it an impulse. An impulse. In other words, a change in momentum can be imparted by an impulse. So I know I'm throwing a lot of terms at you, but it's just a couple of mathematical equations. Momentum is mass times your velocity or speed. A change in momentum is a force applied over a time, and we call that an impulse, the change in momentum. It's just given a name. So we could actually set up our equation like this. If impulse is force times time, and if impulse means change in momentum, you guys know from math class that we can use the delta symbol to mean change. So if momentum is mass times velocity, we could show change in velocity as being a delta times mv. But remember from earlier, we said mass doesn't usually change. So a lot of times what you'll do is you'll see this equation slightly rearranged like this. It'll say force times time equals mass times the change in speed or velocity. Since mass probably doesn't change, like if you're pushing a car, the mass of the car is not going to change. There's no need to put it inside of the parentheses there after the delta symbol. Okay, what can we learn from this equation? What it's telling us is force times time is change in momentum. You can get a very large change in speed or velocity on something by having a large impulse. The way to get a large impulse is to either have large force or a large time or both. So let's say you want to hit a baseball and you want to hit it a really long way. What you want to do is try to apply the maximum force that you can hit it with, but you also want to extend that over the longest time. So if you can hit the ball and follow the ball with the bat for a short, at least for a little while, you can keep applying a force to the ball over a longer period of time, then the ball's speed will change a lot more. It'll probably go farther, assuming you hit it up high enough, you might get a home run. Same sort of logic you apply to other sports, like, say, golf. You want to hit your golf ball a long way. What you want to do is try to hit it as hard as possible, have as big a F as possible, but also stay in contact with the ball as long as possible. Now, if you took slow motion video of, say, a golf club hitting a golf ball, I don't know if you can see this picture if you're using a phone, you might not be able to see it very well, but the ball is actually misshapen at this point, at the point of impact. So what you want to do is try to follow the ball right off of the tee until it springs back into shape and leaves the club. So if you're swinging the club, you don't want to just hit it very hard. You want to swing it very fast and try to keep up with the ball. And as long as you stay in contact with the ball, you keep imparting a force. So it's like pushing the car example earlier. If you push it twice as long, you'll get twice as much change in momentum. In other words, the mass doesn't change, you'll get twice as much change in speed. And speed is what you want if you want the ball to go a long way. Now, in that particular example, because the ball was misshapen and then it kind of springs back into shape and you're not always in the same amount of contact with it, the forces involved during a collision like this actually change over that brief instant of time. But for your purposes and my purposes, any kind of problem that we give you, we're going to assume that we're just going to look at the average force. We're not going to talk about changes in force during the actual contact. So while the golf club strikes the golf ball, exerts zero force until it comes in contact with it. Then it increases rapidly as the ball becomes misshapen and distorted, then diminishes as the ball comes up to speed. We won't worry about all those various changes. We're just going to call it an average force or a net force, okay? So let's say you're in a car and it's out of control and you had to choose between hitting a haystack or a wall. Which would you choose? Well, I hope that if you could actually control your car, you would go to the haystack. Why? Well, if you hit a haystack at a high speed and you want your speed to go to zero, then you want your impulse to extend over a long period of time. That way your force won't have to be very high, and hopefully it won't hurt your car. You understand? A change in momentum. We want that car's momentum to go to zero. You can do that either by changing the force on the car or the amount of time that the force is applied. So if we apply a long period of time of contact with the car, then the force won't have to be so high. On the other hand, if you were to run into the wall, your time would be very, very short. That means to get this car to go to zero, it's going to require the same change in momentum as hitting a haystack, but it's going to require a large force in this case, which is not going to be pleasant. So in either case, the point was that the car had a certain amount of momentum. If you want that momentum to change and go to zero, then you got to look at both force and time. And sometimes what you want to do is have as small a force as possible. That means you want as big a time as possible. So the same impulse or change in momentum does not mean the same force or the same amount of time. It's the same product of those two quantities, meaning you could vary either one and get the same result. Okay? To keep a force small, you want to extend the time. This has all kinds of implications. For example, if you ever were to go to a circus, you might see the circus has these safety nets set up underneath, say, the trapeze artist. And the point is that they fall into the net, but then the net gives. The net moves from its original position and gives over time. And that way the force on the body is not so great. So a safety net has a small stopping force over a long period of time. It has some give in the stretchiness that makes it extend over a long period of time. So if you extend the time, you reduce the amount of force. Same thing, same principle applies. Like with airbags, the whole point of an airbag is if you get in a collision, the airbag is deployed very, very quickly before your body can hit something. Hopefully, you hit the airbag, but the airbag is not solid. It has basically a hole in it, or really a lot of holes in it. And so, as your body hits it, the air comes out and it starts to deflate. But what that does is it extends the amount of time that your body takes to slow down. So, because your body slows down over a long period of time, the amount of force on your body at any given moment can be reduced. Same thing if you're catching a ball. If you ever played, say, baseball or softball and somebody throws the ball really hard, you don't stick your hand out there and just try to hold it steady. What you do is you try to get the ball in the glove and then move your hand backwards with the ball. What you're doing is making that time of contact larger. And when time goes up, force goes down, and that way it doesn't hurt your hand so much. But it still stops the ball. You can either have a large force or a short time, or a small force and a large time. Okay, it's up to you what you choose, I guess. A couple other examples. If you ever jumped off of something, you might notice that it hurts a lot less if you bend your knees. And that's because you're actually stopping your body over a longer period of time. And so the amount of force is reduced. If you ever are in, say, wrestling or judo, then they teach you when you hit the mat to try to sort of roll with it. And what you're basically doing is extending your time of impact, and that reduces the force on any given part of your body. One last example here. So here's a boxer, and somebody's punching him. Well, if he moves his head backwards as he's getting punched, if he sees it coming and he moves his head backwards, then he extends the amount of time and that lowers the force. Okay, because his his head's going to come to a stop. His head's going to change momentum, but if he changes it over a long period of time, then the force is a lot less. On the other hand, if he misjudges it and leans right into the punch, now his head's going to come to a stop in a short amount of time. He's going to get a large force, and that might knock him out. So it's an actual direct or indirect relationship here, inverse between force and time, and it's exact. So if a boxer is able to make contact time 5 times longer by riding with the punch, how much will the force be reduced? The answer is it'll be 5 times less. It's exactly inverse. If one goes up, the other goes down by the exact same proportion. Here's another example, I guess. I'm not done with examples, am I? If you drop something, have you ever noticed that sometimes it breaks? Well, what happened was a large force was applied over a short period of time. If you could extend the time, then the force goes down. The force that it's getting hit with goes down, and it might be able to withstand that. So if you drop it onto say a concrete floor, then the time of impact is going to be very short. If you drop it onto a carpet, the carpet has some give to it and it slows down over a short period of time, but it's still a lot longer period of time than if it just hits, say, a concrete floor. So it might survive if it hits a carpet. Okay, so the glass might be able to withstand a small force, whereas it'll almost certainly break if a large force is applied. So here's a question for you. I'm not making these into Ed puzzles or Desmos today because I do have a homework assignment for you. So we'll just get our grade by doing your homework. When a dish falls, will the impulse be less if it lands on a carpet than if it lands on a hard floor? Impulse is change in momentum. So which will be less, landing on a carpet or landing on a hard floor? I wish I'd made that into a poll because it'd be interesting to see if you understand. They would be the same. The impulse is a change in momentum. It would come to a stop in either case. So the amount of change would be the same. The question is, would it break or not? And that's a question of how much time does it require to stop. But the actual impulse or change in momentum is going to be the same. It's going to go to zero velocity. The mass is going to stay the same. So the change in momentum is force times time. And your question really is, would it break or not? And that's a question of how much force gets applied. So let me do one kind of a little bit more complicated problem for you to show you how this works. Let's say we have a 1 kilogram object and it's initially going at, say, 10 meters per second. So this is like, say, a baseball. And if you catch it and bring it to a stop in 0.2 seconds, what net force did you apply to make it stop? Well, what you do with a problem like this, with any physics problem, the best thing to do after you read the problem is to start writing down what you know. The 1 kilogram is a mass. 10 meters per second is a speed. Now, it's not just any speed. It says it's the initial speed. So I'm going to list that as VI. Then it comes to a stop. You didn't see a number there, but you have to recognize that anytime something comes to a stop, that means its final speed is 0. So I'm going to put that as a VF. 0.2 seconds is obviously a time. And it says, what net force did you apply? So I'm going to write that down too. I'm going to put F equals question mark. Now what you do once you get all the knowns and unknowns written down like this is you look for equations that have these variables in it. You don't necessarily need all of the variables, all of the measurements to answer the question. That's going to take a little bit of experience doing problems to figure out which equation you need. But in this case, since we know we're talking about momentum and impulse, I'm going to look up my momentum and impulse equations. I put them there on the top. Impulse is force times time, or impulse, force times time, is a change in momentum, mass times a change in speed. So I recognize here that I have mass, I have time, and if I take VF minus VI, I have a change in speed. So it looks like that last equation is the one that I need. Force times time equals mass times the change in velocity or speed. Now, I don't want force times time. What I want is just F. So what I have to do is just divide both sides by T. So force equals mass times the change in speed divided by time. Now it's just a matter of plug and chug. Again, kind of a rookie mistake that a lot of people make is they just write down the numbers, or they don't write anything down. They just get their calculator out. Let me recommend against that. Slow down and write it down. I would write F equals 1.0 kilograms times 0 minus 10.0 meter per second. Okay, do you realize why I put it like that? Because the final time, change in speed is final minus initial. The final speed is 0. So it should be 0 minus 10, not the other way around. You don't put the big number first, you put the last number first. And final means it stopped in this case. And then we're going to divide that by 0.20 seconds. So if you do that calculation, it's 1 times a minus 10 divided by 0.2. That's minus 50. It's not 50, it's minus 50. And the units don't cancel out. We have kilograms times meters per second. Then that's all divided by seconds. Well, you may recognize the kilogram meter per second is the same thing as kilogram meter per second squared, which is the same thing as a Newton. Now, I know we haven't done a lot of problems, but you just kind of have to get used to that. That sometimes units, if you have compound units, they have other names, and we call it the Newton. If you left it as kilogram meter per second, then that would also be correct. But we usually refer to force units as newtons in the metric system. So the answer is minus 50. Now, why is it minus 50? It's because the force you're applying is in the opposite direction that the object is moving. You're trying to bring it to a stop. So that makes sense. If we call the way it's moving positive, then the force has to be applied in the negative direction. But again, just don't freak out if you run into a complicated problem. Write it down. Write all your units. Find a formula that works. Write all the units as you work, and you'll be able to work it out. And when you get the right units, you know you probably did the problem correctly. So there's my answer, minus 50 newtons. One last little topic, a little twist on this impulse idea. If you ever watch something hit the ground, let's say, like the dish earlier, then you may notice most of the time those things bounce. Well, that actually requires a greater change in momentum, or in other words, a greater impulse. Think about this. Let's say that a flower pot is knocked off and is falling down towards you. If you catch it, you change its momentum, then that requires a certain amount of impulse. If you took that flower pot and you threw it upwards, you would change its momentum again. That would require a certain amount of impulse. So if that flower pot comes down and bounces off of your head, even though you didn't intend to throw it up, you in fact imparted more momentum. So it had some momentum coming down and hit you. It comes to a stop and then goes back up because it bounces. That actually would hurt you more because it would have more change in momentum than if it just came to a stop. So it's just something to think about, that if you make something bounce, that's actually two changes in momentum. You add them together, in a sense, you get a greater change in momentum that way. What that implies is if it's a greater change in momentum, it could be a greater change in force. Remember, momentum change is force times time. So you could get hurt a lot more if something bounces. Or you could make use of that fact. Here is a person who's breaking some bricks. Wouldn't you be allowed to be able to do that? But if you ever watched somebody do this, then they're trained to hit it and then allow their hand to bounce back up rather than follow through. So in this particular case, the way you want to change the momentum of the bricks the most is by making your hand bounce, because that way you get a momentum change of your hand down and a momentum change of your hand up, and that could impart a large force. Here's one last little practical application of this. Back in the old days, you guys in history class, maybe you hear about the gold rush in California in 1849. Well, there were other gold rushes before that. That's why the one in 1849 was made such great history, is that other people had already tried to find gold in other parts of the country. And so when they heard there was gold in California, all those gold miners all gathered up from these other places and all rushed out there. And so it became a really big gold rush. But the point is that one of the ways to do that, if you had a big gold mining operation, was to operate a well, a machine of some sort to help you sift through all the material, and they would use a water wheel like this. But it turns out this is not a very efficient design, because the water hits it and then bounces right down. It just pushes the wheel down. The water goes down with it. After the gold rush, about 25 years later, a fellow by the name of Lester A. Pelton designed this water wheel. Now the water goes down, hits it, and bounces back up. Because the water bounces back up, it actually imparts a greater force. And so this water wheel will spin faster and will operate machinery much more efficiently. So it's called the Pelton water wheel. Just a little history fact for you, but it's a use of physics.